Earthquakes are natural disasters that strike with little warning, often causing immense destruction and loss of life. The quest for earthquake prediction has captivated scientists, policymakers, and the public for centuries. Knowing when and where an earthquake will occur could save countless lives and reduce the economic impact of these seismic events. However, despite advancements in our understanding of the Earth's inner workings, predicting earthquakes with precision remains an elusive goal. In this article, we will explore the fascinating world of earthquake prediction, its challenges, and the ongoing research that offers hope for a safer future. Chapter 1: The Earth's Restless Interior. To understand earthquake prediction, we must first delve into the Earth's inner workings. Our planet is not a static sphere. It is a dynamic, ever-changing entity. Beneath its solid surface lies a complex and restless interior. The Earth's interior is divided into several layers, including the inner core, outer core, mantle, and crust. The interaction between these layers creates the conditions for earthquakes. 1.1. Plate tectonics, the driving force. The key to understanding earthquake prediction lies in plate tectonics, a groundbreaking theory that revolutionized geology. Plate tectonics explains the movement of the Earth's lithosphere, which is divided into large, rigid plates that float on the semi-fluid asthenosphere beneath them. These plates are constantly in motion, driven by the convective flow of the mantle. Plate boundaries are where much of the seismic activity occurs. 1.2. Faults. Where stress is released. Earthquakes occur along faults, fractures in the Earth's crust where rocks have moved relative to each other. There are three main types of faults. 1.2.1. Normal faults. These occur when the Earth's crust is stretched, causing one side to drop relative to the other. 1.2.2. Reverse faults. These occur when the Earth's crust is compressed, causing one side to be pushed up relative to the other. 1.2.3. Strike-slip faults. These occur when rocks on either side of the fault move horizontally past each other. 1.3. Stress accumulation and release. The Earth's lithospheric plates are constantly in motion, and as they interact at plate boundaries, stress builds up along faults. This stress is released in the form of seismic energy when the friction holding rocks together is overcome. This sudden release of energy causes the ground to shake, resulting in an earthquake. Chapter 2: Early Attempts at Earthquake Prediction. 2.1. Historical methods. Throughout history, people have attempted to predict earthquakes using a variety of methods, often based on superstition or anecdotal observations. Some of these early methods included 2.1.1. Animal behavior. Some cultures believed that unusual animal behavior, such as erratic movements or strange sounds, foretold an impending earthquake. 2.1.2. Celestial events. Eclipses, meteor showers, and comet appearances were often thought to be harbingers of earthquakes. 2.1.3. Earthquake clouds. Unusual cloud formations were sometimes associated with earthquakes, though this connection lacked scientific basis. 2.2. Early scientific efforts. As our understanding of geology and seismology grew, so did the pursuit of more scientific earthquake prediction methods. In the 19th and early 20th centuries, seismologists began to collect data from earthquakes and analyze patterns. While these efforts were significant steps forward, they were far from providing reliable earthquake predictions. Chapter 3: Modern Earthquake Prediction Techniques. 3.1. Seismometers, detecting the shakes. The development of seismometers revolutionized our ability to monitor earthquakes. Seismometers are instruments that record ground motion caused by seismic waves. By analyzing the data from seismometer networks, scientists can pinpoint the location, depth, and magnitude of earthquakes within minutes of their occurrence. 3.2. Foreshocks and aftershocks. One promising avenue for earthquake prediction is the study of foreshocks and aftershocks. Foreshocks are smaller earthquakes that occur before a larger main shock, while aftershocks follow a main shock. Some researchers believe that patterns of foreshocks may provide clues about when a larger earthquake is imminent. 3.3. GPS and strain accumulation. Global Positioning System (GPS) technology allows scientists to measure the slow movement of tectonic plates over time. By tracking the accumulation of strain along fault lines, researchers can estimate the potential for future earthquakes. However, this method cannot provide precise timing. Chapter 4: Earthquake Early Warning Systems. 4.1. Early Warning in Action. Earthquake early warning systems have been implemented in several earthquake-prone regions worldwide. These systems use seismometer data to detect the initial, less destructive P waves of an earthquake before the more damaging S waves and surface waves arrive. This allows for seconds to minutes of warning, which can be crucial for public safety. 4.2. Limitations of early warning. While earthquake early warning systems are valuable tools, they have limitations. The amount of warning time is often very short, and it may not be enough to prevent all damage or provide adequate time for evacuation. Additionally, false alarms can erode public trust in these systems. Chapter 5: The Holy Grail of Earthquake Prediction, Long-Term Forecasting. 5.1. Long-term versus short-term prediction. Long-term earthquake prediction aims to forecast seismic events on a scale of years to decades, providing communities with ample time to prepare. Short-term prediction, on the other hand, seeks to forecast earthquakes on the scale of hours to days and is more challenging due to the complexity of seismic processes.